Okay. Uh, Good afternoon, everybody. Good morning to those west of Mountain Daylight Time here. My name is Larry Van Bussum. I'm with the National Weather Service here at the National Interagency Fire Center in Boise, Idaho. I'd like to welcome you to the September version of Fire on the Fives. We did put it off a little bit. This is being recorded on the 15th of September 2015 due to some high fire activity earlier in the month. So we want to thank you all for showing up um, for today's presentation. Our guest speaker today is Matt Fearon, and Matt is from the Desert Research Institute in Reno, Nevada, and he will be talking to us about establishing a national standard methodology for mixing height. With that, I am going to turn it over to Matt, but before I do, I want to remind folks that please, if you put your phone on mute, to make sure that you mute your microphone and not put us on hold. And with that, we will turn it over to Matt.
All right, thank you, Larry. I appreciate the introduction, and I appreciate the opportunity to give this presentation today. Some of you may have seen this already. I gave it in Minneapolis, Minnesota back in May. And it's not very long. I want to say it's probably 20 or 25 minutes, plus or minus. But it's basically looking at establishing a national standard methodology for mixing height. And so my co-authors Tim Brown and Gary Curcio also helped a lot with this study. It was kind of piecemeal over a series of months and maybe even a couple of years. Some of it stems from my master's degree, and it's kind of a consolidation of all the mixing height pieces that I've looked at over the years. And it's kind of combining 4 different methods that could be used in operations. Some are more simple than others. And I try to show basically, the advantages and disadvantages of all 4, and kind of make a recommendation at the end. So this first graph here is just a look at the convective boundary layer over a given day, and anywhere in the CONUS. And you can just see the mixing light layer, which many of you know, just basically is more a function of heating, but can also be a function of what's going on with the wind shear. And it just shows the diurnal cycle and kind of a little definition of what the mixed layer is, and it's a function of thermodynamic and dynamic processes. The idea behind this study and the importance, I just kind of, in this next slide, laid out a few examples of what that could be. It's important for smoke management, prescribed fire, and wildfire programs. It goes into determining burn decisions, go versus no-go. It also assesses smoke dispersion from wildland fire. It can be used to determine permissible forest fuels on a given day. And it's also for mixing height is important when you have fire and you have smoke. There's often sensitive areas, and you kind of want to know what the mixed layer height would be, because that then can give you an idea of how those places might be impacted. Some of the motivation behind this study is to get a national standard. Basically, there's a bunch of ways to compute the mixed layer, and sometimes when you use different methods, you get results that are different. They're not drastically different, but sometimes they can be, and you get mixed layer heights that vary. Some are lower, some are higher, and it's important for different people that are using the mixing height value to have some kind of consistency across. It's helpful for their planning and use. The method that's, I think, probably used the most by the Weather Service and maybe a bunch of different agencies that also compute mixing height is the Holsworth method, and that's kind of been around since the 60s and uses a dry environment, a thermodynamic surface parcel. It's a pretty simple method. It's quick and easy, but through this study you'll see that the heights tend to be kind of a slight underestimate of what the mixing height typically could be, and it's mostly because it doesn't incorporate moisture into the calculation. And then also the motivation is there's a lot of prescribed burn opportunities, and if you have a robust method that not only accommodates the convective portion of the mixed layer growth, but also the dynamical things that are going on. If you have a front or something, or you have some kind of wind shear going on, it's important to have both of those in the calculation. So that's kind of the motivation behind doing all this and looking at these methods. So here's kind of the first two. These are the static stability or convective boundary layer looks that just rely on temperature with Holsworth, and then also temperature and mixing ratio with the Stoll method. They're really very similar. They're almost the same method. The Stoll method gives you a little more look at the stability, and because it looks at the entire profile versus just looking at the surface parcel and what that's doing. But the Stoll method also separates itself because it includes the mixing ratio in its calculation. So you typically, when you look at this graph here to the right where it shows the blue Holsworth and then the, I guess that's a pinkish red for the Stoll, you see that there's a slight, height discrepancy, and that's because of the moisture that's included in the Stoll method. But they're very similar. The procedures are very similar. And so one could easily swap out and use the Stoll method if they just wanted to include moisture. And I know there's some issues with software and how they get the virtual potential temperature, but I don't know if it would be that difficult. It's just a matter of how someone might do that. So, and I know that varies. This next slide shows the two other methods, the Richardson number, which has also been around even longer than any of the Stoll or Holsworth methods, and the turbulent kinetic energy, which is pretty complicated to calculate, but nowadays, I mean, most people are looking at numerical model output anyway, and I know they run operationally the NAM North American model is, I think, down to 4 or 5 kilometers over the CONUS, which is pretty fine resolution that actually spits out a TKE-based mixing height. I think they call it PBL height. They also spit out a mixing height value that's associated with the Richardson number, and it's already pre-computed and available. And this slide just outlines how to compute the both terms and basically what they're a function of. The Richardson number is a function of basically the convection and shear, the ratio of the two. And it's a pretty simple method, but it gets at static and dynamic processes with the one number. And then on the right-hand side is the TKE, which is more complicated, but it just kind of breaks it down a little bit here, and it shows you what it's a function of. It's the convection of the mean wind. It's got the buoyancy, it's got the shear, it's got transport, and a bunch of other little terms. It's also got the viscous dissipation rate through the column. And both these methods, basically, you look from the ground up through the profile, and I've got two kind of thresholds I'm using. That can vary a little bit. It sort of depends. I just found these in some studies, and they worked good in my study. For Richardson, I'm using a value which is unitless of 0.505, and for TKE, it's 0.1 joules per kilogram that I chose. And I put the references down there at the bottom if anyone's interested. So this little study I did, it used 2 years worth of data, and I used the RUC2 model output just because it covered from 2009 through 2010, and it had TKE available. I could get the actual analysis from the model, not using forecasts, which was important for me. And I could compute all 4 methods with it. I could get the TKE, the Holsworth, Stoll, and Richardson number. So I computed that for 2 years at select grid points over the CONUS. And then also it was important that I use that RUC because it aligned nicely with using what I also used to compute mixing height was the Calypso LiDAR, which is a NASA product. And there's a bunch of pieces to that, but I used the aerosol component, which basically looks at the aerosol through the column, and where that terminates, basically where there's usually a pretty sharp line where that terminates. And I was able to define the mixed layer that way, just as a proxy, as kind of an observed value to compare to the other 4 methods. And I also did not use radiosondes in this study, even though they're really good tools, just because I wanted to get more spatial coverage, and I could really align the model and the Calypso quite well with each other, and then get more points rather than using the radiosondes. So this next slide shows kind of a little example of how the mixing height is computed from Calypso. And the left panel there is just a browse image of the different identifications from Calypso. There's cloud, there's aerosol. You can tell where the clear air is, the surface. So you can kind of see there those black profiles are attenuated, but they're likely probably convection. And then on the far left, I have a little example of a black line that shows where I estimated mixing height from the orange, which is the aerosol. And then if you look to the right panel, basically that one little sliver is comprised of 15 individual profiles that make up basically a 5-kilometer swath of the Calypso. And so from that profile there on the right, I was able to pick off the mixing height, which is just over 2 kilometers in this particular example. So this is just kind of a way to show you what I did to get at the mixed layer as a proxy for observed. And then this next slide shows the data overlay. The green points are the Calypso points that cover the conus, or even extend beyond and below. The blue points, which are real fine, you can't even really see the separation, is the Ruck points, the Ruck 2 points. And then you can see in the yellow where the radiosondes were over the conus. And you can see there's just not that good of alignment with the Calypso. So not that I wouldn't use them to compute mixing height, they're very good tools, but in just this particular study I wanted to try something different with the Calypso. So that's why I didn't use them. This next example here, this next slide, is an example of how I compute mixing height from most of the methods. I couldn't put TKE and RI on here even though I put the values in there. But the left-hand bottom there shows basically a Calypso value from the orange, the aerosol value of just under 2.5 kilometers. And then on the right you see potential temperature and virtual potential temperature from Holsworth Stull and how you get the mixing height from there. And then I also imported the Richardson number and the TKE. And so this is for the same example, and you can see the 5 different methods and the difference in all the different mixing height values you get. And there's quite a range, with Holsworth being kind of the lowest, or actually in this case Richardson number is the lowest, and then Holsworth, and then TKE and Stull. So, but you can see TKE and Stull are pretty close, which remains consistent as I look at mixing height across the conus and at different times. They're usually quite close, especially if you can use a fine resolution model to get TKE. In this case, Calypso is a little higher, and it tends to be typically a little higher, and I think that has to do with the way the aerosol is captured at the top of the boundary layer. Sometimes it's a real sharp line, which is great because that's a real good indicator, but sometimes that line is a little diffuse, and so I think you get a little bit of an overestimate sometimes with the Calypso. And in this case, you can see there's about maybe 200 or 300 meters there. Might be a little too high. So this next slide is basically a comparison of all the methods against what the LiDAR would predict. And this is combining the 2 years of data. I can't remember the exact value of points that are in here, but it's over 2,000 points where I computed mixing height. And you can kind of just see the range of the methods compared to LiDAR. So TKE and Richardson number are probably pretty close. Stull also right there. And then you can see Holsworth is slightly lower than all the methods. One thing you can see about Stull and Richardson numbers, there's a bit more variance in the box plot. But still, the median value there, the black line, is pretty consistent across TKE, Stull, and Richardson, with Holsworth kind of a little bit lower. And then again, the LiDAR is a little bit higher, but I think that's that diffuse line where the aerosol terminates at the top. So this next slide is basically the same kind of thing, just as a scatter plot. where the LiDAR's on the x-axis and the methods are on the y. And I show them for each one, TKE, Stull, RI, and Holsworth. And you can see the variance there with the Richardson and Stull a little bit, but not as much. And if you look at TKE and you look at all the methods, there's a kind of a clustering at the bottom there where they kind of well predict the lower values, but then as you get out, they kind of spread. And then in Stull and Holsworth, there's kind of a linear relationship along the x-axis. And I think that just has to do with the method being so sensitive to the surface parcel. And if there's any kind of a slight inversion, that may classify a real low mixing height from that particular method, whereas the TKE and the Richardson number are not going to be so held against that inversion. Even if it's really minor, that can happen, and you can get, and it's probably something that may mix out in a couple hours, but it's really sensitive to that surface parcel, and so with the TKE and the Richardson number, you don't get that sensitivity. It's kind of removed, which makes those methods a little more beneficial. Plus, you also get the dynamic stability in those calculations, which I think is a little bit better to include both rather than just one. This next example shows some results of the study as well, kind of from the spatial view. And here I have basically a wharf model simulation at 2 kilometers. On the left panel shows the difference between TKE and Stull and the spatial difference. And then when it's red in that plot, that's where TKE is actually greater, which happens most of the time. But then if you look in the center panel, that's a breakdown of all the methods, or I'm sorry, of all the terms that go into TKE. The B is the buoyancy term, the S is the shear, the B plus S, which is blue, which is a combination of both buoyancy and shear. And then there's an advection terrain component. And you can just see how the TKE is sort of behaving in this case and why, which term is sort of driving at why the height is slightly greater. Kind of down in the southeast there corner of Minnesota, you can see the reddish popping up as buoyancy, and then there's a little bit of black, which is kind of advection. And then kind of up in the northwest there in North Dakota, you can see the blue, greens, and shears dominating, but then also buoyancy and shear are contributing. And then you can also kind of relate that to the right panel, which is basically the terrain with the 850 millibar flow laid on top. And you can kind of see the flow kind of corresponds to these things as you kind of look at them. So I just thought it was a nice example of space in breaking down which components of the TKE are actually driving the mixed layer and why the TKE in this case is much greater than the Stull method. So this next slide is kind of a summary of all the methods, and I tried to lay out the advantages and the disadvantages of each, because nothing's perfect. I know at the end here I'm going to sort of advocate that the TKE is better just because it includes all terms that basically drive the mixed layer. But again, it has some disadvantages. It's more complicated. It requires a model. But like I said earlier in the presentation, the NAM model actually has the PBL height, which is a form of the TKE estimate of the mixed layer. And so that might be something that could be experimented with and used initially because it's simple, rather than just taking the TKE profile and computing it, from scratch. But then as you look at some of these other methods, they all have their pluses and minuses. I'll start at the bottom with Holsworth. It's easy and simple to compute, and all you need is the temperature. It doesn't require a model. You can just use any kind of a sounding from a radiosonde. But then it has some faults. I mean, it only looks at the surface parcel, which again can be sensitive to minor inversions that may mix out. And most forecasters probably will see that in advance, and that wouldn't be an issue anyway. But it also doesn't look at perturbation terms, which if you're just looking at mean flow versus little perturbations that can jump through the day, which the TKE considers, and the Richardson number could consider if the bulk form was not used. And then the Stoll kind of has the same advantages and disadvantages of as Holsworth, only it includes the moisture, which is kind of a big deal. So you got another simple method there, but now you're looking at kind of an unsaturated moist atmosphere. And you can use that whether it's completely dry or there is some moisture. It's not going to hurt the calculation. It can only help if you're actually looking when there's moisture or not. So, and then the bulk Richardson number is again another. It has some good advantages and it has some disadvantages. It also doesn't require a model. It can be computed from a sounding. It's a little more involved, as you might remember from the equation I laid out earlier, but it's not that technical. And it looks at the whole convective and dynamic components, and so that makes it sort of attractive, and it's simpler. And it is basically a small subversion of the TKE. So it's another avenue to try. But then the TKE is probably the best because it just includes everything. It includes the buoyancy, shear, advection, influences of the terrain, and you need a fine resolution model, though, however, to get at that. So those are kind of the bullet points of a paper that I've put together with Tim Brown and Gary Curcio. And there's been some other folks that have reviewed the paper, which I've thanked in the paper. And it's in press now with the Journal of Operational Meteorology. I believe I'm working with a technical editor. It should probably be in print sometime the end of the month, early October. Just guessing there, but with my interaction with them. So, and all this stuff is in that paper in gory detail. So with all the methods and different analysis looks at them. And I'm hoping that, I recommend that the TKE be used, but hopefully this starts some discussion on kind of making a national standard methodology. So that's really all I had. It was pretty short, but it gets the point across, and I can take any questions that anyone might have.
Matt, this is Larry. I'd like to start out with a question in terms of the validation of these methods. Could you speak a little bit to a little more on why you decided the Calypso data may be a better representation of actual mixing height versus using the sounding?
Sure, yeah. Like I said, the soundings are great, but when you're looking over the whole entire CONUS and say you're looking in the warm season, sometimes, especially on the East Coast and the eastern part of the United States, the soundings are at 0Z, which is a bit later. Sometimes the mix, it still may capture the maximum time the mix layer is growing, but as you get into that fall season or spring season, it may miss that. And I wanted something that was sort of consistent in time across the United States, but then also I wanted something that had more spatial coverage of points that I could then relate to numerical model analyses points. And so the Calypso had that. It had afternoon samples at, across the United States. Usually they were anywhere from local time noon to 3 p.m., 4 p.m. As you got maybe towards the West Coast. So it just had some good temporal and spatial consistency of when the maximum mixing layer would be growing, and it was at a 5-kilometer resolution, which was pretty good compared to the Ruck. I mean, the Ruck was a little coarser, but Those were my ideas and why I chose the Calypso. And I wanted to try something different too, because a lot of people verify with radiosondes. But I just came into this product and I just thought it would be a good proxy for comparison. So I hope that answers your question.
Yeah, it does. I guess one of the other things I had heard, and I'll throw this out here for you to comment on, is that using the Calypso data, you actually were measuring, you were physically measuring the aerosols at the boundary layer. So you were actually getting some sort of independent measure of where that mixing height was, and that maybe one of the fallbacks of using a sounding for verification is the fact that you are verifying the sounding using the exact same method you're using to calculate it with. So you have no actual independent verification on where that mixing height actually lies.
I guess, yeah, I'm not, when I use the LiDAR data, I'm not using the actual method. Is that what you mean?
Correct.
I'm using just the aerosol estimate of what the height would be. Yeah, you're right about that for sure. So, yeah, and maybe if I'd use the sounding and then use the actual method on that, then it would be more direct, one-to-one, I guess. Is that your point, Larry?
Well, more so my point is that maybe one of the things that folks need to watch out for is trying to verify their mixing height by calculating it off of sounding, because essentially all you're doing is just verifying the fact that you made a calculation on a sounding. You're not actually looking at the physical data of where that boundary layer actually is.
Yeah, so the LiDAR kind of gets at that a little bit with the aerosol extent vertically. So anyway.
Okay. Any other questions out there?
There's got to be one.
Yeah, this is Scott in Raleigh. So how would we calculate the TKE via AWIPS? I mean, right now we're using pretty much the stall method to calculate the mixing heights around here.
Okay. Yeah, I guess I'm not familiar totally with AWIPS. I kind of have a general idea of how it works, but I guess that would be a question for me back to you. Would be, do you have access to NAM model grids in your AWIPS? And number two, if you do you know if there's a variable in that grouping that's called PBL height, or PBLH is the acronym I think it's called?
Number one, yeah, I think we do, and two, I think I do remember seeing a PBL option or item in the browser, possibly. I'll have to look at that.
Okay, and then one other follow-up to that is also there's another term in the NAM output. It's called I think it's MIXHT. That's another variable, and I was curious if that's available in AWIPS, and if it is, that is an estimate of the Richardson number. So I was just thinking, if you have AWIPS and you're looking for a really quick way to get at these TKE or Richardson, you could use those two values, which are based on TKE and Richardson. So.
Okay, you said that was MIXHT?
I believe that's what it was. Yeah, I think that's the acronym.
Okay, thank you.
It's something. If it's not that, it's something very close to that.
Yeah, we've been trying to verify our mixing height forecast here this past late winter through early summer. We were able to get with a air weather squadron down at Fort Bragg and able to get some extra soundings from Greensboro, and we released those soundings between 18 and 19Z in the afternoon.
Oh, that's a perfect time, yeah.
And we were going back and look. Because of funds and limited access, we only did maybe 10 to 12 studies.
Yeah.
And we're still looking at that. We're still looking at the data right now to see how well the stall method was doing, and how well our forecasts are actually verifying.
That sounds like a pretty interesting study. It'd be neat to compare that to what I was doing too.
Sure, but again, I mean, you had 2,000 points. We've had 12. So.
Oh, still though, that's
pretty rough.
Yeah.
So that everybody on the call knows, this is Heath Hockenberry from Boise.
Robin Heffernan is actually leading a grids requirement to examine the national methodology that we use for smoke grid production. There was actually a presentation at this week's Sioux conference that I saw through email from Bill LaPenta, the NCEP director, about gaining requirements for air quality in general. So we have opportunities to provide our requirements to NCEP. We've talked pretty directly with Jeff Demego about the Richardson Number methodology originally used to determine PBL, and provided feedback that that might not be the most accurate method. The second thing I wanted to mention is the idea that's kind of come out from the University of Utah about utilizing ceilometers or some kind of fixed ground-based way of detecting particulate matter to determine mixing height. I was curious if people on the call, if we got away more from determining mixing height from manual determination from soundings and move more towards a particulate height collection method or verification method where that particulate was observed over a particular spot and integrated across the country, what people thought of that type of way to verify what the mixing height is in terms of concentration of aerosols. Heath, I'll just say a quick point. I think I've heard of that method from Utah using the ceilometers, and I think that would be a great way to get at the mixing height. Probably better than these particular methods I've outlined. So that's just my 2 cents. It's kind of something that I'm thinking of championing, and from a national level. I just am hopeful to get the word out more to the WFOs through the grids team to make sure that everybody knows about this proposal, and as kind of a way to move forward with actually verifying what we're putting into our forecast using aerosol data instead of eyeballing it. It would also be a good way to compare these methods to ceilometer measured mixing heights, too. Yeah. So that people can do side by side with what they're currently doing. Yeah. That's always a good way to move to a new method, is to determine something a little bit differently. Yeah, I don't know how much it would be to outfit either a region or a section of the country to do this measurement, or whether it's available somehow already, but it might be something worth our while.
Hi, Heath.
Yep.
Hey, this is George Matthews, Morristown, Tennessee.
Hey.
Yeah, that'd be great. That's one of the questions I was going to ask, is verification, because even in the southeast where the mixing heights aren't as high, we still get a big discontinuity between forecast offices using different tools, etc. And so verification would go a long way toward trying to reel us into something close to truth.
Yeah, aside from putting up more balloons everywhere routinely, something that we're not going to be able to do, perhaps we can use existing locations to determine aerosols somehow. Yeah, so I think we'll have more conversations with U of Utah, and again, there is this grids team that we have together. Robin is leading it, and we're trying to do this with transparency. That we just don't implement something without everybody knowing what's going on. And verification is tops on the list on the appropriate method to use.
So Heath, are the ASOS units already equipped with this sensor, or is this something that has to be added on?
I don't know. I really don't know. That, again, we'll have to explore that with U of Utah and the ASOS program.
Okay.
Hi, this is George Matthews again. Just one quick question, which may be common knowledge to all of you, but if you have a pretty good idea of your cumulus cloud base height, where is that in relation to the mixing height?
I would think that would be quite close, actually, to where the mixing height would be the base of the cumulus. I mean, maybe slightly into that layer, but I would say that's a really good estimate. If you can pick that off and know that height, that would be a really good estimate of mixed layer height.
Okay, all right, very good. Yeah, it seems like there's some very old but tried and true methods for calculating, and with your temperature and dew point, you get a pretty good estimate of your cumulus height in the afternoon. All right, thanks.
Yeah, that in combination with the ceilometer might be, kind of the two of them together might be pretty interesting.
Any other questions?
This is Tim Destry at the New Orleans Baton Rouge Forecast Office. I just wanted to also throw out there also that make sure people are aware of all the soundings that are available from MD CARS, MD CRS, which is available on AWIPS just at New Orleans, which is not anywhere close to a larger airport. There's probably sometimes a couple dozen soundings there throughout the day. Not all of them have the moisture profile, probably only maybe 5–10% of them have that. But I can imagine some larger airports get probably dozens of aircraft soundings per day.
Okay, anyone else? Okay, well, again, I want to thank everybody for attending, and thank you to Matt for presenting on this. And we will get an announcement out about the next Fire on the Fives, which should be on or around October 5th. And this presentation was recorded. We'll put it onto our Fire Weather Fire on the Fives site, Google Sites, and get that information out to you. Again, thanks very much, and have a great day.
Thank you, Larry. Appreciate it.